some of the questions, but it is cumulative as opposed to being completely different. So we're looking at the sum of two or more Poisson distributions today, and how we would be able to do that. Okay, so there's a little blurby thing here about cars going in and out of a village, and it tells you on average, at 3 p.m. for an hour, there are 3.5 cars per minute going into the town, and there's 5.7 cars per minute leaving a town. Okay. It says, assuming that the flow of vehicles into and out of town can be modelled by independent Poisson distributions, you can model the flows of vehicles in both directions as follows. So we've got let X represent the number of vehicles into town, let Y represent the number of vehicles out, and T represent the total of X and Y. To find the probability of T, they've suggested that we could look at the probability of X and Y and all the different combinations. So if I want the probability of a total cars going in and out being 0, I would need the probability of 0 cars entering and 0 cars leaving. Okay? And then with those probabilities, you would times it together because it's a probability of this and this. So that's a multiplicative probability calculation. So for when I do the probability total 1, there's two scenarios that you need to consider. 1 car entering, no cars leaving, or 1 car leaving, no cars entering. So you do the probability of this times this, probability of that times that, add them together. Okay. However, as we start to add more numbers on, it becomes more and more complicated. Okay. As soon as we start to get to 2, it goes from 2 calculations to, I think there's 3 calculations there. And if we move this to 3, it's going to be more, because the amount of combinations, because you'll get your 0 with 3, your 1 with 2, your 2 with 1. It's that expansive, like what's that thing called? The triangle, Pascal's triangle. Yeah, I think it's the Pascal's triangle situation. Your NCR concepts that you would end up with, and it's just more and more calculations. However, actually, one of the things that is good with Poisson is that if you are combining 2 Poisson distributions, rather than calculating each probability for the separate distributions and combining them that way, you can combine the mean. Okay, because the mean is independent and random. Because it's independent and random, you can combine those 2 values together. Okay, so if you think about the mean number of cars leaving being, 3.5, and the mean number of cars entering being, mean number of cars entering being 3.5 and leaving 5.7, in total cars are leaving, in total distribution of cars would be 9.2. Okay, about 9.2 cars per minute doing something. Okay, so we're able to set up a Poisson distribution based upon that using these 2 values, and they go into the actual written notification of this. So like if X is Poisson Y and Y is Poisson mu, then X plus Y is Poisson Y plus mu. Okay, it's just saying if I've got this distribution and this distribution, I can add the means together, and that makes my life way easier. Cool. So they've done the calculations there, and if you look at the 2 values, the one where they did it long way and the one where they did it the combined way, exact same numbers. It's it's just their proof of that, and we don't need to focus too much on the proof. All we need to do is be able to focus on these things. So it says a rare disease causes of death on average of 2 people per year in Sweden, 0.8 in Norway, 0.5 in Finland. As far as is known, the disease strikes at random and cases are independent of one another, unlike something else which is going on at the moment. What is the probability of 4 more deaths from a disease in these 3 countries? So all you need to identify is that because they're independent and random, you can combine those 3 events. Okay, so the total number of deaths would be 3.3, as stated on the just on the overall mean. Okay, So when we do the Poisson distribution, we just need to consider 3.3. So any questions that we answer for this, whatever the R value, your lambda would be 3.3. Cool? Easy. They've got another example, something to do with a lonely road in Scotland. I don't know why it has to be Lonely Highland Road. Why can't it have a friend? Cars are observed passing at a rate of 6 per day, and lorries at a rate of 3 per day. On the road is an old cattle grate. Will soon need repair. The local works department decide that if the probability of more than 2 vehicles passing per hour is less than 1%, so the probability of more than 2 vehicles passing per hour is less than 1%, then repairs to the cattle grid can wait until next spring. Okay, so they're saying, you know, if it's really unlikely the cars will go over this grate, they don't need to fix it right away. They can wait till a later date to actually repair this situation. Okay. Otherwise, it'll have to be repaired straight away. When will the cattle grid have to be repaired? Will it have to be in the winter or the spring? So, what do you have to consider here? What's our overall lambda? What's the lambda for this question? 9? Is it 9? 0.375. If you've read ahead, why is that the case? Or if you worked it out? Per hour. Good. So don't forget time and space. We need to take that into consideration. The means they gave us were per day, and then this question was about per hour. So they often do that. They will often change the time, but not make it super obvious that they've changed the time. They are, yeah. They're making you pay attention. That's what they try to do. But so they're going to add the 2 means together, the 3 and the 9 together, and then you could divide by 24. Or you could do the 3 divided by 24 and the 6 divided by 24 and then add it together. It's the same value in this case. In certain other questions, they may give you 2 different distributions with 2 different times. So then you'd have to consider the scalar on both individually first before adding it together. So just be careful of that. So I'm not going to do the maths here, but yep, you get the combined distribution being lambda 0.375. And then it's just about using that value to calculate the probability they've suggested. So they've done the shortened version of Poisson, which the other day we didn't actually look at the shortened version, and for some reason it's the first time they kind of introduce it in this textbook, but they don't explain it in any way. That was the recursive table formula, but this is actually better in terms of recursive nature for this. So let me just go through what we've got. So instead of e to the 0.375 being your e to the y, e to the minus lambda, okay? What they've done, instead of timesing by lambda to power r over r factorial, and then added each one subsequent where the r is increasing, what they've done is they've said, actually, because it's always e to the minus lambda, and because I'm going to be adding another e to the minus lambda times lambda to power r minus 1 or something over r minus 1 factorial, I can actually factorize this and take the e to the minus lambda on the outside, say lambda r over r factorial plus lambda r minus 1 over r minus 1 factorial. I know we tend to write that as an increasing one, but just because I'll be able to define this a bit easier, being when r equals 1 stop, I'm writing it that way, okay? But basically a factorized version of it, and that's what they've written, except they've not written their full working out for it. They've just gone straight to the, oh, I know the first thing's going to be 1, the second thing's going to be 0.375, and then it's 0.375 squared over 2, and so on and so forth. So they've been lazy with their working out in the book. So just wanted to make sure that we were aware of what's going on there. So in reality, what they did was 0.375 to power 0 over 0 factorial plus 0.375 to power 1 over 1 factorial plus 0.375 to power 2 over 2 factorial. Actually, I think that is better. I know the other day I said I prefer to see it written out fully, but the factorized version works way better. It's way quicker. Okay. Because they were looking at the greater than, they need to do 1 minus just because. In fact, do they do 2 factorial?
Yes.
Is 2 not inclusive? Oh, it's greater than 2. Does it just say more than 2? More than 2. So yeah, 3 or more. Okay. So they only went up to 2, took that away from 1. That's the answer. Okay, cool. Hopefully that's a shorter explanation from me today. Yeah, that's it's under 15 minutes. Look at that. Woo, you can actually do some questions today. Yes.